Carbon dioxide. From essential to excessive. The complete story, the invisible architect. Imagine a gas so vital that without it, Earth would be a frozen, lifeless rock. Imagine the same gas becoming so abundant that it threatens to unravel the climate stability that allowed human civilization to flourish. Imagine a molecule so simple, just one carbon atom bonded to two oxygen atoms, yet so powerful it shapes the fate of our planet. Right now, with every breath you exhale, you're releasing carbon dioxide into the atmosphere. Plants around you are absorbing it, using it to build their bodies through photosynthesis. The ocean is dissolving it, changing its chemistry in ways that ripple through marine ecosystems. The atmosphere is accumulating it at rates unprecedented in human history, trapping heat and altering climate patterns worldwide. This is the story of carbon dioxide, Earth's climate thermostat. It's a tale of ancient ice cores revealing planetary secrets, scientists who connected invisible gases to global temperatures, and a growing understanding of how human activities have seized control of a process that once operated on geological timescales. By the time we're done, you'll understand what CO2 is, why it matters so profoundly, how we've transformed its atmospheric concentration, and what this means for Earth's future. This is the story of the molecule at the center of the climate crisis, and it's more fascinating than you might think. Part 1. The gas that built our world, the invisible foundation for most of human history. We had no idea carbon dioxide existed. It's invisible, odorless at normal concentrations, and seems utterly unremarkable. Air feels like nothing. How could we know it contained a molecule that determined whether Earth was habitable? The discovery came gradually. In the 1750s, Scottish chemist Joseph Black identified what he called fixed air, a gas that extinguished flames and was exhaled by breathing animals. It was heavier than ordinary air and could be collected above fermenting beer or by treating chalk with acid. Black had discovered carbon dioxide, though he didn't call it that yet. Over the following decades, scientists realized this gas was everywhere. It bubbled from the ground in volcanic regions. It was produced when things burned or decayed. It was released by breathing animals and absorbed by growing plants. It was, in fact, a fundamental player in the cycles of life and death, but nobody yet understood its most important property. Carbon dioxide was a greenhouse gas. It trapped heat, and the amount of CO2 in the atmosphere determined, more than anything else except the sun itself, what Earth's temperature would be. The greenhouse effect revealed. The story of understanding carbon dioxide's climate role begins with light and heat. Sunlight passes relatively easily through the atmosphere, warming Earth's surface. The warm surface then radiates energy back towards space, but not as visible light as infrared radiation, invisible heat energy. In 1856, American scientist Eunice Foote conducted experiments showing that CO2 absorbed heat more effectively than ordinary air. She hypothesized that changes in atmospheric CO2 could affect Earth's temperature. Her work went largely unnoticed at the time. A few years later, Irish physicist John Tyndall performed more detailed experiments, measuring how different gases absorbed infrared radiation. He discovered that water vapor and CO2 were particularly effective at trapping heat, while oxygen and nitrogen, which make up most of the atmosphere, were nearly transparent to infrared radiation. Tyndall realized these greenhouse gases were like a blanket around Earth. Without them, the planet would be frozen. With too much, it would overheat. The amount of CO2 in the atmosphere, he understood, was crucial to Earth's climate. Then, in 1896, Swedish chemist Svante Arrhenius made a remarkable calculation. He estimated that doubling atmospheric CO2 would raise global temperatures by several degrees Celsius. He even speculated that human coal burning might eventually alter climate, though he thought this would take thousands of years and might be beneficial for northern regions. Arrhenius had identified the mechanism. More CO2 means more heat trapped in the lower atmosphere. He couldn't know that humans would increase CO2 far faster than he imagined, or that the consequences would be far more complex than simple warming. Life's carbon cycle. To understand what we've done to atmospheric CO2, we first need to understand the natural carbon cycle. The movement of carbon between atmosphere, oceans, land, and living things. Plants are carbon's primary harvesters. Through photosynthesis, they take CO2 from air, combine it with water using sunlight's energy, and build it into sugars, starches, and cellulose. Every leaf, every trunk, every root is built from carbon that was once atmospheric. CO2. Forests are vast stores of carbon pulled from the sky. Animals participate by eating plants or other animals, using the carbon for their own bodies and burning some for energy. This burning cellular respiration combines carbon with oxygen, releasing CO2 back to the atmosphere. Breathing out is releasing carbon back to the sky. When organisms die, decomposers break them down, and most carbon returns to the atmosphere as CO2. But sometimes, under the right conditions, organic matter gets buried before it can decompose. Over millions of years, heat and pressure transform this buried carbon into fossil fuels: coal, oil, and natural gas. This carbon is effectively removed from the active cycle, locked underground. The ocean plays a crucial role. CO2 dissolves in seawater, some of it forming carbonates that eventually become limestone. Marine organisms use carbon to build shells and skeletons. When they die, some of this carbon settles to the ocean floor, locking it away for millennia. Volcanic activity and rock weathering complete the cycle. Volcanoes release CO2 from Earth's interior. Chemical weathering of rocks slowly consumes CO2 from the atmosphere. These processes operate on geological timescales, hundreds of thousands to millions of years. For hundreds of thousands of years before humans began burning fossil fuels, this cycle was roughly in balance. CO2 fluctuated naturally, but within a range that kept climate relatively stable. The residence time of a CO2 molecule in the atmosphere averaged hundreds to thousands of years before natural processes removed it. This balance wasn't static, it varied with ice ages and warm periods, with the growth and decay of forests, with ocean circulation changes. But the variations were slow and reversible. The system had time to adjust. Until we arrived. Part 2. Measuring the invisible, the Keeling Curve, Earth's vital sign. The modern era of CO2 monitoring begins with Charles David Keeling, a young geochemist, who, in 1958, began making precise measurements of atmospheric CO2 concentration atop Mauna Loa volcano in Hawaii. Keeling chose Mauna Loa carefully. He needed a location far from forests, cities, and other local CO2 sources. He needed clean air representing the average state of the atmosphere. The high-altitude volcanic peak in the middle of the Pacific Ocean was perfect. Month after month, year after year, Keeling and his colleagues measured CO2 concentration with painstaking precision. The data revealed two remarkable patterns. First, CO2 concentration oscillated annually, rising during Northern Hemisphere winter and falling during summer. This reflected the seasonal breathing of forest CO2 released by decay when leaves fell. Carbon dioxide absorbed when growth resumed each spring. The planet itself was breathing. Second, and more ominously, CO2 was rising. Each year's peak was higher than the previous year's. Each year's minimum exceeded the previous year's minimum. The jagged line showing annual oscillations was mounted on an inexorable upward trend. The Keeling Curve, as it became known, provided the first unambiguous evidence that human activities were changing atmosphere composition on a global scale. When Keeling began measurements in 1958, CO2 concentration was about 315 parts per million ppm. Today it exceeds 420 ppm. The curve continues its relentless climb. This simple graph became one of the most important scientific measurements of the 20th century. It documented, with absolute clarity, that humans were conducting an unprecedented experiment with Earth's atmosphere. There could be no debate about whether CO2 was rising. Keeling's instruments recorded it happening in real time. Ancient air, ice core records, but Keeling's measurements only went back to 1958. What about earlier? How did CO2 vary before human influence? To answer these questions, scientists turn to an unlikely source: ancient ice. In Greenland and Antarctica, Snow accumulates year after year, compressing into ice that preserves air bubbles from when the snow fell. These bubbles are tiny time capsules, containing atmospheric samples from thousands of years ago. Scientists drill deep into ice sheets, extracting ice cores that stretch back hundreds of thousands of years. By analyzing air and bubbles at different depths, they reconstruct atmospheric CO2 concentration throughout Earth's recent geological history. The ice cores revealed several crucial facts. First, CO2 concentration varied naturally, oscillating between about 180 ppm during ice ages and 280 ppm during warm, interglacial periods like the one in which human civilization developed. Second, these natural variations occurred slowly, over many thousands of years, following the rhythm of orbital changes that triggered ice age cycles. The system had time to adjust as CO2 rose and fell. Third, current CO2 levels far exceed anything seen in at least 800,000 years of ice core records. The rapid rise to over 420 ppm is unprecedented in this entire period. We've pushed CO2 well beyond the natural range. Asterisk. Fourth, temperature and CO2 correlated closely throughout the ice core record. When CO2 was high, temperatures were warm. When CO2 was low, ice ages gripped the planet. The relationship was clear and consistent. CO2 concentration and global temperature moved together. This correlation didn't prove causation by itself, but it fit perfectly with the greenhouse effect physics. CO2 was acting as Earth's thermostat, just as Arrhenius had theorized. The ice cores provided the long-term context showing how abnormal our current situation truly is. The carbon budget. Tracking the sources modern science doesn't just measure atmospheric CO2, it tracks where it comes from and where it goes. This accounting, called the carbon budget, reveals the sources of the problem and the scale of the challenge. The primary source of rising CO2 is burning fossil fuels. When we burn coal, oil, or natural gas, we're taking carbon that was locked underground for millions of years and releasing it to the atmosphere as CO2. Globally, fossil fuel combustion releases about 35 to 40 billion tons of CO2 annually. Land use change, particularly deforestation, contributes additional CO2. When forests are cleared, the carbon stored in trees either burns, releasing CO2 immediately, or decays, releasing CO2 over years. Deforestation and land use contribute roughly 5 to 6 billion tons of CO2 yearly. So humans are releasing about 40 to 45 billion tons of CO2 annually. But atmospheric CO2 doesn't increase by that full amount. What happens to the rest? About half of human CO2 emissions remain in the atmosphere, driving the increase measured by stations like Mauna Loa. The other half is absorbed by natural sinks, primarily the ocean and land vegetation. The ocean absorbs roughly 10 billion tons of carbon annually, dissolving CO2 into seawater. This is good for atmospheric CO2 levels but problematic for ocean chemistry. As we'll discuss later, land ecosystems, primarily forests, absorb another 12 to 15 billion tons annually. Growing forests pull CO2 from air and store it in wood. This terrestrial carbon sink partially offsets deforestation and acts as a brake on atmospheric CO2 rise. These natural sinks are doing us an enormous favor, absorbing about half of our emissions. Without them, atmospheric CO2 would be rising twice as fast. But there's no guarantee these sinks will continue functioning at current rates as climate changes. If they weaken or reverse, atmospheric CO2 could accelerate even faster. Multiple lines of evidence. How do scientists know increased atmospheric CO2 comes from burning fossil fuels rather than natural sources like volcanoes or ocean outgassing? Multiple independent lines of evidence point to the same conclusion. First, the isotopic composition of atmospheric CO2 is changing. Carbon comes in different isotopes, primarily carbon-12 and carbon-13. Fossil fuels are depleted in carbon-13 relative to atmospheric CO2. As fossil fuel burning increases, atmospheric CO2 becomes more depleted in carbon-13, exactly as expected if fossil fuels are the source. Second, Atmospheric oxygen is decreasing at exactly the rate predicted by fossil fuel combustion. Burning fossil fuels consumes oxygen, producing CO2. Measurements show oxygen declining in precise proportion to CO2 increasing, confirming combustion as the source. Third, emissions from fossil fuels can be calculated independently from production data how much coal, oil, and gas is extracted and burned. These calculations match atmospheric measurements. The amount of CO2 added to the atmosphere equals the amount we're releasing through fossil fuel burning and deforestation. Fourth, natural sources like volcanoes emit far too little CO2 to account for the observed increase. All volcanic activity globally releases roughly 1% of what humans emit through fossil fuel burning. Natural sources simply aren't large enough. The evidence is overwhelming and consistent. Increased atmospheric CO2 comes from human activities, primarily fossil fuel combustion. There's no scientific debate about this. The multiple lines of evidence all point to the same conclusion. Part 3. The physics of warming. How CO2 traps heat. Understanding why CO2 matters requires understanding how greenhouse gases trap heat. It's a straightforward physics problem, well understood for over a century. Sunlight, primarily visible and ultraviolet light, passes through the atmosphere relatively easily and warms Earth's surface. The warm surface radiates energy back toward space, but not as visible light. Instead, it radiates infrared energy, heat energy with longer wavelengths than visible light. Greenhouse gases are transparent to visible light, but absorb infrared radiation. When a CO2 molecule absorbs infrared energy, it vibrates more energetically, then re-emits the energy in a random direction. Some goes to space, some goes back toward the surface. This process happens countless times. Infrared energy emitted by Earth's surface gets absorbed and re-emitted repeatedly by greenhouse gas molecules, bouncing around in the lower atmosphere before eventually escaping to space. This delays the energy's escape, keeping the lower atmosphere warmer than it would be otherwise. More greenhouse gases means more absorption and re-emission. Greater delay before energy escapes, warmer lower atmosphere. It's that simple. Double CO2 concentration and you enhance this process, trapping more heat. The physics is well established and has been confirmed by detailed observations from satellites and ground-based instruments. We can directly measure the change in infrared radiation. Escaping to space as CO2 increases, it matches theoretical predictions precisely. Climate sensitivity. How much warming? Knowing that more CO2 causes warming doesn't immediately tell us how much. The direct effect of doubling CO2 with nothing else changing would warm Earth by about 1.2 degrees Celsius, 2.2 degrees Fahrenheit. That's the basic physics of CO2's greenhouse effect. But Earth's climate doesn't work in isolation. Warming triggers feedback changes that amplify or dampen the initial warming. Understanding these feedbacks is crucial for projecting future climate change. The most important positive feedback involves water vapor. Warm air holds more water vapor than cold air. As CO2 warms the atmosphere, it increases water vapor content. Water vapor is itself a powerful greenhouse gas, so this amplifies warming. The initial CO2-driven warming gets magnified by the water vapor feedback. Ice-albedo. Feedback also amplifies warming. Ice and snow reflect sunlight back to space. As warming melts ice and snow, darker land or ocean is exposed. These darker surfaces absorb more sunlight, warming further, melting more ice. This positive feedback is particularly important in polar regions. Cloud feedbacks are complex and uncertain. Warming changes cloud coverage, height, and properties. Some cloud changes amplify warming, others dampen it. How clouds respond to warming remains a major uncertainty in climate projections. When all feedbacks are included, the best estimate is that doubling Co-A leads to warming of A-4 degrees Celsius. Y-7.2 degrees Fahrenheit. With a likely range of A-5 degrees Celsius, this is called equilibrium climate sensitivity. How much warming occurs once the climate system fully adjusts to doubled CO2? The uncertainty range might seem large, but notice what it doesn't include. the possibility that doubling CO2 causes little or no warming. The physics and observations rule out low sensitivity. The question is whether warming will be moderately bad or very bad, not whether it will occur beyond temperature. Compound changes. Global warming from CO2 doesn't just mean higher temperatures. It triggers cascading changes throughout the climate system. Precipitation patterns shift. A warmer atmosphere holds more moisture, potentially leading to more intense rainfall when it occurs. But warming also increases evaporation, potentially intensifying droughts between rain events. The result is a tendency toward both more intense wet extremes and more severe droughts. Storm intensity changes. Warmer oceans provide more energy for hurricanes and typhoons. While the total number of tropical cyclones might not increase dramatically, the strongest storms likely become more intense, with higher wind speeds and heavier rainfall. Ocean circulation changes. As the Arctic warms faster than the tropics, temperature gradients that drive ocean currents may weaken. Changes to the Atlantic meridional overturning circulation, including the Gulf Stream, could significantly affect regional climates, particularly in Europe and North America. The cryosphere Earth's ice responds dramatically. Glaciers worldwide are retreating. Arctic sea ice is declining. The Greenland and Antarctic ice sheets are losing mass. These changes don't just affect local regions. They influence global sea level, ocean circulation, and climate patterns. Ecosystems shift. As climate zones move poleward and upward in elevation, ecosystems must migrate or adapt. Many species can't migrate fast enough to keep pace with changing climate. The result is ecosystem disruption, range contractions, and potential extinctions. All these changes are connected. They interact, sometimes amplifying each other, creating the complex picture of climate change we observe. CO2 doesn't just turn up the temperature dial, it reorganizes the entire climate system. Asterisk sea level. The delayed response, perhaps no consequence of CO2-driven warming, is more consequential than sea level rise. Currently, sea level is rising at about 3 to 4 millimeters per year, and the rate is accelerating. Sea level rises for two main reasons. First, warming ocean water expands. Thermal expansion. As the ocean absorbs heat from the warming atmosphere, its volume increases. This thermal expansion has contributed roughly 1/3 to 1/2 of observed sea level rise so far. Second, land-based ice melts. Glaciers worldwide are retreating, transferring water from land to ocean. The Greenland ice sheet is losing mass at accelerating rates. Even the Antarctic ice sheet, once thought stable, is contributing to sea level rise, particularly from the vulnerable West Antarctic ice sheet. The crucial point is that sea level rise has enormous inertia. Even if we stopped emitting CO2 immediately, sea level would continue rising for centuries due to the slow response of ice sheets and deep ocean warming. The ocean takes centuries to millennia to fully warm in response to changed atmospheric conditions. Ice sheets respond on similar timescales. Current sea level rise measured in millimeters per year seems manageable. But we're committing to future rise measured in meters. Every ton of CO2 we emit contributes to sea level rise that will continue for centuries. Major coastal cities worldwide face eventual inundation unless emissions decline rapidly. Projections vary depending on emission scenarios and ice sheet behavior. But multi-meter sea level rise over coming centuries is increasingly likely unless emissions drop dramatically. Low-lying island nations and coastal regions worldwide face existential threats. Part 4. The ocean's other CO2 problem: ocean acidification. The evil twin. While much attention focuses on carbon dioxide's role in warming, the ocean faces another CO2 problem: acidification. About 1/4 of human CO2 emissions are absorbed by the ocean, and this absorption is changing ocean chemistry in ways that threaten marine life. When CO2 dissolves in seawater, it forms carbonic acid. This increases the ocean's acidity, or, more precisely, decreases its pH. Since the Industrial Revolution, ocean surface pH has dropped by about 0.1 units, representing a 30% increase in acidity. This might sound small, but it's rapid and significant for marine organisms. Many marine organisms build shells or skeletons from calcium carbonate. This includes corals, shellfish, some plankton, and many other species. Ocean acidification makes it more difficult for these organisms to build and maintain their calcium carbonate structures. In sufficiently acidic water, these structures can even dissolve. The impact cascades through marine food webs. Pteropods, tiny swimming snails, are important prey for many fish. Acidification threatens pteropods. Corals build reefs that provide habitat for countless species. Acidification weakens corals and can prevent reef building. Shellfish industries face direct threats as oysters, clams, and mussels struggle in more acidic water. Unlike ocean warming, which can potentially be partially reversed if CO2 levels decline, ocean acidification is directly tied to atmospheric CO2 concentration. The ocean will remain acidified as long as atmospheric CO2 remains elevated. Reducing acidification requires reducing atmospheric CO2. This presents a dilemma. The ocean's absorption of CO2 helps slow atmospheric accumulation and warming, but it simultaneously drives acidification. The ocean is taking a hit to protect the atmosphere and, by extension, U.S. Coral reefs. Sentinels of change. Coral reefs illustrate the combined threat of warming and acidification. Corals are vulnerable to both. Ocean warming causes coral bleaching. Corals live in symbiosis with algae that provide food through photosynthesis. When water gets too warm, corals expel their algae, turning white, bleaching. Bleached corals aren't dead, but they're stressed and vulnerable. If heat stress continues too long, corals die. Massive bleaching events have become more frequent and severe. The Great Barrier Reef experienced catastrophic bleaching in 2016, 2017, 2020, and 2022, 4 events in 7 years. Recovery between events is incomplete, leading to net reef decline. Meanwhile, ocean acidification makes it harder for corals to build their calcium carbonate skeletons. Even if corals survive heat stress, acidification undermines their structural foundation. The combination of warming and acidification creates a squeeze that threatens reefs globally. Coral reefs support perhaps 1/4 of all marine species, despite occupying less than 1% of ocean area. They provide coastal protection, support fishing industries, and generate tourism revenue. Their decline represents ecological catastrophe and economic loss. Some coral species and reef locations are more resilient than others. Conservation efforts focus on protecting resilient reefs, assisting coral adaptation, and reducing non-climate stressors. But ultimately, coral reef survival depends on limiting both warming and acidification, which means limiting CO2 emissions. Ocean circulation changes. Rising CO2 doesn't just warm and acidify the ocean, it may alter ocean circulation patterns that distribute heat globally and influence climate. Of particular concern is the Atlantic Meridional Overturning Circulation, AMOC, including the Gulf Stream. This circulation brings warm water northward, releasing heat to the atmosphere, then sinking in the North Atlantic as it cools and becomes denser. The deep water flows southward, eventually returning to the surface and completing the cycle. This circulation is driven by temperature and salinity differences. Warming Arctic regions and increased freshwater input from melting ice can reduce the density differences that drive circulation. Some models and observations suggest AMOC is weakening. Significant AMOC slowdown would have major climate implications. Europe would cool despite global warming, as less heat is transported northward. Sea level would rise along the U.S. East Coast. Tropical rainfall patterns would shift. The consequences would be global. Current evidence shows some AMOC weakening, but uncertainty about future trends and impacts. Climate models disagree about how much weakening to expect. Abrupt AMOC collapse depicted dramatically in movies but unlikely in the near term would require extreme conditions. However, ocean circulation changes illustrate that climate response to rising CO2 involves reorganization, not just uniform warming. Regional effects can differ dramatically from global trends. Understanding these regional patterns is crucial for adaptation planning. Part 5. The historical context CO2 through Earth's history. Today's CO2 levels, while unprecedented in human history, aren't unprecedented in Earth's geological history. Understanding the deeper past provides context and warnings. During the Eocene epoch, roughly 50 million years ago, atmospheric CO2 was much higher than today, perhaps 1,150 ppm or more. Earth had no permanent ice sheets. Forests grew near the poles. Sea level was perhaps 70 meters higher than today. Life thrived, but in a world utterly different from the one in which humans evolved. The Paleocene-Eocene thermal maximum, PETM, about 56 million years ago, provides a particularly relevant example. A massive carbon release, possibly from volcanic activity or methane release from ocean sediments, drove rapid warming of way -8 degrees Celsius globally. The event caused ocean acidification, ecosystem disruption, and species extinctions. Recovery took 100,000 to 200,000 years. The PEPM carbon release totaled perhaps 4,000 to 7,000 gigatons over several thousand years. Humans are releasing carbon at a rate at least 10 times faster. Our current carbon release rate may be unprecedented in Earth's history, certainly unprecedented for tens of millions of years. Importantly, when CO2 was naturally high in Earth's past, climate adjusted over millions of years. Ecosystems evolved and adapted. When CO2 rose rapidly, as during the PTEM, the results included mass extinctions and ecological collapse. Rate of change matters enormously. Modern species, including humans, evolved during a geological period of relatively low, stable CO2 and mild climate. Our agriculture, infrastructure, and civilization developed during an unusually stable climatic period, the Holocene epoch. We're now rapidly exiting that stable state and moving toward conditions not seen for millions of years. The Anthropocene. Human influence. Some scientists argue we've entered a new geological epoch, the Anthropocene, defined by human influence on Earth's systems. No signature of the Anthropocene is clearer than the CO2 spike. For 10,000 years before industrialization, atmospheric CO2 hovered around 270 to 280 ppm, remarkably stable. This stability was part of what made the Holocene epoch ideal for agriculture and civilization development. Then, beginning in the late 1700s with the Industrial Revolution, the curve bent upward. Initially slowly, just a few ppm over decades, then accelerating. By 1900, CO2 had reached 295 ppm. By 1950, 310 ppm. By 2000, 370 ppm. Today, over 420 ppm. The acceleration parallels human fossil fuel use. As coal powered the Industrial Revolution, then oil powered transportation and petrochemicals, then natural gas expanded, CO2 emissions surged. What took nature millions of years to sequester underground, we're releasing to the atmosphere in centuries. This rapid change leaves a clear geological signature. Future geologists studying ice cores or sediment layers will see an abrupt spike in CO2, a shift in carbon isotopes, and evidence of global environmental change, all pointing to the brief moment when one species burned through geological carbon reserves and altered planetary climate. We are, quite literally, writing a new chapter in Earth's geological history. The question is what that chapter will say about our wisdom and our legacy. Learning from paleoclimates. Tuning past climates. Paleoclimatology helps us understand how Earth's system responds to CO2 changes. It provides evidence we can't get from direct observations of current conditions. One key lesson: climate sensitivity to CO2 appears consistent across Earth's history. When CO2 rises, temperature rises. The relationship isn't perfectly linear and varies with initial conditions, but it's remarkably robust. Paleoclimate evidence helps constrain estimates of climate sensitivity. Another lesson: changes can be abrupt. While geological CO2 changes are typically slow, the climate system can flip relatively rapidly between states. Ice ages ended with abrupt warming over decades to centuries, rapid on geological timescales. Though slower than current changes, paleoclimate also shows that high CO2 states are incompatible with large ice sheets. When CO2 has been high in the past, ice sheets didn't exist. This tells us that if we maintain high CO2 levels, ice sheets will eventually disappear, even if this takes centuries or millennia. The eventual consequence is locked in. Finally, paleoclimate shows that ecosystems track climate. When climate changed in the past, species migrated, ecosystems reorganized, and some species went extinct. The difference now is that we're driving change far faster, and human land use blocks many migration routes. The stress on ecosystems is unprecedented. Part 6. Sources and solutions. Where CO2 comes from. Understanding emission sources is essential for addressing the problem. Different sources require different solutions. Energy production, about 40% of emissions. Burning coal, natural gas, and oil to generate electricity. Power plants are the largest single source category. The solution pathway is clear: renewable energy, solar, wind, and nuclear power, combined with energy storage and grid improvements. Transportation, about 25% of emissions, gasoline and diesel. For cars, trucks, ships, and aircraft. Electrification works for many vehicles but is challenging for long-distance trucking and aviation. Solutions include electric vehicles, improved public transit, biofuels, and eventually hydrogen or synthetic fuels for aviation. Industry, about 20% of emissions. Manufacturing processes, particularly cement and steel production. These emissions are harder to eliminate because they often come from chemical processes, not just energy use. Solutions include process innovations, material substitution, and carbon capture. Buildings, about 6% of emissions. Heating, cooling, and appliances. In residential and commercial buildings, solutions include better insulation, heat pumps, efficient appliances, and electrification of heating. Agriculture, about 10% of emissions, including CO2, methane, and nitrous oxide. Emissions from livestock, rice cultivation, fertilizer use, and agricultural machinery. Solutions include improved practices, dietary changes, and alternative proteins. Deforestation, 5 to 6 billion tons CO2 annually, clearing forests for agriculture. The solution is ending deforestation and reforestation where possible. No single solution addresses all sources. A comprehensive approach requires transforming energy systems, transportation, industrial processes, agriculture, and land use simultaneously. It's an enormous undertaking but technically feasible with current and emerging technologies. The removal challenge. Even with aggressive emission reductions, some scientists argue we'll need to actively remove CO2 from the atmosphere to limit warming to relatively safe levels. This is called carbon dioxide removal, CDR, or negative emissions. Nature-based CDR includes reforestation, forest management, soil carbon enhancement, and wetland restoration. These approaches are relatively low cost and provide co-benefits but have limited scalability and permanence challenges. Technological CDR includes direct air capture, machines that chemically capture CO2 from air, and bioenergy with carbon capture. And storage, growing plants, burning them for energy, capturing the CO2, and storing it underground. These can potentially scale large but are currently expensive and energy-intensive. Ocean-based CDR includes approaches like ocean alkalization or growing seaweed, but these are largely experimental with uncertain effectiveness and potential side effects. The challenge is scale. Humanity currently emits about 40 billion tons of CO2 annually. Even reducing emissions by 90% would still require removing perhaps 4 billion tons annually to reach net zero. That's orders of magnitude beyond current CDR deployment. CDR shouldn't be seen as an alternative to emission reductions, it's a supplement to them. The priority must be preventing emissions. Every ton we don't emit is a ton we don't need to remove later. And removal is far more expensive and difficult than prevention. The policy landscape addressing CO2 emissions requires policy interventions at multiple scales: international, national, and local. The Paris Agreement 2015 committed countries to limiting warming to well below 2 degrees Celsius and pursuing efforts to limit it to 1.5 degrees Celsius. Countries submitted nationally determined contributions, NDCs, outlining emission reduction plans. However, RENTNDCs are insufficient to meet temperature targets, a gap between commitments and requirements. Policy tools include carbon pricing, carbon taxes or cap-and-trade systems, regulations, efficiency standards, emission limits, subsidies for clean energy and electric vehicles, investment in research and development, and phase-outs of fossil fuel subsidies. Some jurisdictions have implemented effective policies. The European Union has a carbon trading system. Many countries subsidize renewable energy. California has comprehensive climate policies combining multiple approaches. China is investing massively in renewable energy and electric vehicles. However, global progress remains insufficient. CO2 emissions continue rising, though growth has slowed. The gap between current trajectory and what's needed to limit warming is large. Closing this gap requires stronger policies, faster technology deployment, and sustained political will. The policy challenge is complicated by equity concerns. Developed nations produced most historical emissions while developing nations face impacts and need energy for development. Climate finance funding from developed to developing countries for mitigation and adaptation is a critical but contentious issue. Technology and innovation. Technology advancement is crucial for addressing CO2 emissions affordably. Key areas include renewable energy. Solar and wind costs have plummeted, now competing with or beating fossil fuels in many regions. Continued improvement in efficiency and cost, plus better energy storage, will accelerate adoption. Batteries and storage. Energy storage is essential for managing intermittent renewables. Battery costs have dropped dramatically and continue improving. Grid-scale storage is increasingly viable. Electric vehicles. EV technology is maturing rapidly. As batteries improve and charging infrastructure expands, EVs will increasingly compete with and replace internal combustion vehicles. Industrial processes. Innovations in cement, steel, and chemical production can reduce process emissions. Green hydrogen produced with renewable electricity could replace fossil fuels in some industrial applications. Carbon capture. While currently expensive, carbon capture technology is improving. For some emission sources like cement production, capture may be the only viable mitigation approach. Advanced nuclear. New reactor designs promise safer, more efficient nuclear power. If deployed successfully, nuclear could play a significant role in decarbonizing electricity generation. Synthetic fuels. For applications where electrification is difficult, aviation, some industrial processes, synthetic fuels created using captured CO2 and renewable energy might eventually provide low-carbon alternatives. Technology alone won't solve the problem. Deployment requires policy support, investment, and behavior change. But technology makes solutions more affordable and feasible, expanding what's politically and economically possible. Part 7. Living in the CO2 era. Attribution science. Connecting cause and effect. As extreme weather events increase, heat waves, droughts, floods, hurricanes, a key question arises. Which events are caused or worsened by CO2-driven climate change? Attribution science uses climate models to compare the actual world with a hypothetical world without human greenhouse gas emissions. By running many simulations with and without CO2 increases, scientists can estimate how much human influence change the probability or intensity of specific events. Results show clear patterns. Heat waves are strongly attributable to CO2-driven warming. Many recent heat waves would have been virtually impossible without human-caused climate change. Droughts show moderate to strong attribution, particularly when intensified by high temperatures. Heavy precipitation events show attribution because warmer air holds more moisture. Hurricane intensification shows emerging attribution signals as warming oceans provide more energy. Attribution science has progressed from asking, is climate change happening, To how much did climate change contribute to this specific event? The answer is increasingly, significantly. While not every extreme event is caused by CO2, most are made worse, more intense, more likely, or more prolonged. This has practical implications. Understanding attribution helps communities prepare for future risks, informs insurance and risk management, and potentially provides basis for climate-related liability claims. Adaptation. Living with changes already locked in even if emissions stopped immediately. Significant climate change is already locked in due to CO2 already in the atmosphere and ocean heat uptake lag. Adaptation, adjusting to climate impacts, is essential alongside mitigation. Coastal regions face rising seas. Adaptation includes building seawalls, elevating structures, improving drainage, restoring coastal wetlands, and managed retreat from the most vulnerable areas. Some communities are already relocating. Agriculture must adapt to shifting growing seasons, changed precipitation patterns, and new pest ranges. Adaptation includes crop diversification, new crop varieties, improved irrigation efficiency, and adjusting planting schedules. Water management must address changing precipitation patterns and increased drought and flood risks. Adaptation includes improving water storage, enhancing efficiency, developing drought-resistant landscaping, and integrated watershed management. Public health systems must prepare for heat-related illness, changing disease patterns, air quality impacts, and mental health effects. Adaptation includes early warning systems, cooling centers, improved disease surveillance, and climate-aware health planning. Infrastructure must become climate resilient. This includes designing for higher temperatures, heavier rainfall, stronger storms, and sea level rise. Roads, bridges, power grids, and water systems all need upgrading. Ecosystems need assisted adaptation. Conservation corridors allow species migration. Protecting climate refugia preserves havens for vulnerable species. Ecosystem restoration improves resilience. In some cases, assisted migration of species may be necessary. Adaptation costs money but far less than damages from inaction. For every dollar spent on adaptation, studies estimate savings of $4 to $7 in avoided damages. Early adaptation is more cost-effective than reactive responses after disasters. However, adaptation has limits. Beyond certain warming levels, some impacts become impossible to adapt to, entire island nations disappearing, regions becoming uninhabitable, ecosystem collapse. This makes emission reduction urgent. Adaptation buys time, but can't substitute for mitigation. Individual and collective action. Climate change can feel overwhelming, leaving individuals wondering what they can do. The answer involves both personal actions and systemic change advocacy. Personal carbon footprint reduction includes energy efficiency, renewable energy adoption, transportation choices, walking, cycling, public transit, electric vehicles. Dietary changes, reducing meat consumption, consumption reduction, and sustainable product choices. These actions matter individually small but collectively significant. However, individual action alone won't solve the problem. Systemic change requires collective action, voting for climate-aware leaders, advocating for policy changes, supporting climate organizations, divesting from fossil fuels, and pressuring corporations and institutions to change practices. Climate communication matters enormously. Discussing climate change with friends, family, and communities spreads awareness and normalizes climate concern. Social norms shift through conversation. When people see others taking climate seriously, they're more likely to themselves. Professional influence amplifies impact. Whatever your profession, there are likely ways to integrate climate considerations. Engineers can design sustainable systems. Teachers can incorporate climate education. Healthcare professionals can address climate health connections. Business leaders can implement sustainable practices. Everyone has leverage in their professional sphere. Community resilience building prepares for impacts while reducing emissions. Community gardens, local renewable energy projects, climate emergency response planning. and mutual aid networks all strengthen communities while addressing climate. The goal isn't perfection, it's progress. Every emission reduced matters. Every conversation about climate matters. Every policy change matters. The cumulative effect of millions of people taking action, combined with systemic policy changes, can bend the emissions curve downward. The psychology of climate change understanding. The psychological dimensions of climate change helps explain why responding has been so difficult and how to communicate more effectively. Psychological distance makes climate change feel remote, distant in time, space, or relevance. Future generations seem abstract. Impacts in other countries feel disconnected. The response: make it local and immediate. Discuss impacts happening now, in your region, affecting people like you. System 1 versus System 2 thinking. Our intuitive system. System 1 didn't evolve to respond to slow, probabilistic, global threats. It responds to immediate, visible dangers. Climate requires analytical thinking. System 2. The response: connect climate to immediate concerns, health, economy, security. Cognitive dissonance creates discomfort when behavior conflicts with values. People who care about the future but maintain high-carbon lifestyles experience tension. Rather than changing behavior, they might rationalize or avoid thinking about it. The response: make low-carbon choices easier and more appealing. Doom and gloom messaging can backfire, leading to paralysis or denial. If problems seem hopeless, why bother? The response: acknowledge the serious problem but emphasize agency, solutions, and progress. Hope is essential for action. Identity and values shape climate views more than information does. Climate often becomes politicized, tied to cultural identity. Facts alone don't change minds. The response: frame climate through diverse value systems. Conservatives might respond to stewardship, energy independence, or economic opportunity. Liberals might respond to justice and equity. Religious communities might respond to creation care. Social norms powerfully influence behavior. When people perceive climate action as normal and expected, they're more likely to act. The response: make climate action visible. Discuss it. Normalize it. Create communities of practice. Effective climate communication acknowledges these psychological factors. It's not just about providing information, it's about making climate personally relevant, emotionally resonant, solution-oriented, and socially normalized. Part 8. The path forward. What different warming levels mean. International climate discussions focus on limiting warming to specific levels: -1.5 degrees Celsius, 2 degrees Celsius, or higher. What do these numbers actually mean? 1.5 degrees Celsius warming. Current trajectory has us exceeding this soon. Significant impacts but somewhat manageable. Coral reefs face severe decline but some survival. Arctic sea ice summer minimum still occurs occasionally. Extreme heat, drought, and flood events increase but remain within adaptation capacity for most regions. Some ecosystem loss but not wholesale collapse. Sea level rise of 0.5 to 1 meter by 2100. Several meters over centuries. 2 degrees Celsius warming, likely if current policies continue. More severe impacts. Most coral reefs die. Arctic regularly ice-free in summer. Heat extremes become severe across large regions. Some areas experience water scarcity affecting millions. Agricultural disruption in many regions. Sea level rise of 1 to 2 meters by 2100. With multi-meter rise committed over longer term. Tipping points more likely. 3 degrees Celsius warming, possible on current emissions trajectory. Devastating impacts. Coral reefs functionally extinct. Large ice sheet loss begins irreversibly. Extreme heat makes some currently populated regions nearly uninhabitable during summer. Water crises affect billions. Agricultural disruption threatens food security. Mass ecosystem collapse. Sea level rise of several meters over coming centuries. Multiple tipping points likely crossed. 4 degrees Celsius plus warming, where we head without strong mitigation. Catastrophic. Large-scale ecosystem collapse. Vast regions become too hot for human habitation. Water scarcity affects most major population centers. Agricultural systems collapse in many regions. Mass migration and resource conflicts likely. Civilization threatening. Impacts possible. Sea level rise measured in many meters. The differences between these scenarios are profound. Each half-degree matters. The goal isn't avoiding all impacts. Some are already unavoidable. But limiting impacts to levels we can adapt to while maintaining functioning ecosystems and societies. Tipping points. Points of no return. Climate scientists increasingly worry about tipping points, thresholds where small additional warming triggers large, self-reinforcing changes that become irreversible on human timescales. Ice sheet collapse. The Greenland and West Antarctic ice sheets may have tipping points beyond which they irreversibly lose mass even if warming stops. Crossing these thresholds commits to meters of sea level rise over centuries to millennia. Amazon rainforest evac. The Amazon could reach a tipping point where deforestation plus drought plus fire converts rainforest to savanna. This would release massive carbon stores while eliminating a major carbon sink, amplifying warming. Permafrost thaw. Arctic permafrost contains enormous carbon stores. Warming causes thaw, releasing CO2 and methane, causing more warming, causing more thaw. This positive feedback could accelerate warming substantially. Coral reef death. Coral reefs face a tipping point where warming and acidification cause complete functional collapse. Losing reefs means losing the ecosystems they support and the coastal protection they provide. Ocean circulation shutdown. The AMOC could potentially collapse if weakening reaches a critical threshold, dramatically reorganizing global climate. The concern is cascading tipping points. Crossing one threshold triggers others, creating runaway change. While abrupt, catastrophic cascades are considered unlikely at moderate warming levels. Risk increases with higher warming. Tipping points argue for aggressive mitigation. They introduce tail risks, low probability but catastrophic outcomes. Even if the probability seems small, the consequences are so severe that avoiding them justifies substantial effort. It's like insurance. We pay to avoid catastrophic losses even if they're unlikely. The window of opportunity. Despite the serious situation, we're not doomed. The future isn't predetermined. Actions taken now will shape outcomes for centuries. Emissions are still rising, but growth is slowing. Renewable energy is expanding rapidly. Electric vehicle adoption is accelerating. Awareness is increasing. Climate change is now central to policy discussions worldwide in ways it wasn't decades ago. Progress is real, even if insufficient. The next decade is crucial. Decisions made in the 2020s about energy infrastructure, transportation systems, industrial processes, and land use will determine whether we limit warming to relatively manageable levels or commit to catastrophic change. Infrastructure built now will persist for decades, either locking in emissions or enabling rapid transition. Limiting warming to 1.5 degrees Celsius requires essentially having global emissions by 2030 and reaching net zero by 2050. This is technically possible but requires unprecedented transformation speed. It won't happen through individual action alone. It requires massive policy changes, technology deployment, and economic restructuring. Limiting warming to 2 degrees Celsius requires deep emission cuts by 2030 and net zero by 2070. This is more plausible, but still demands rapid change. Anything less, continuing on current trajectory, leads to 3 degrees Celsius or more of warming with devastating consequences. The physics doesn't negotiate. Every tenth of a degree matters. Every year of delay makes the challenge harder, but the future remains unwritten. We still have agency. The question is whether we'll use it. Reasons for hope. Despite the daunting challenge, there are genuine reasons for hope. Technology is advancing. Solar and wind are now the cheapest energy sources in most markets. Battery costs have dropped 90%. In a decade, electric vehicles are becoming mainstream. Innovation continues accelerating. The technical feasibility of deep decarbonization is increasingly clear. Economics are shifting. Clean energy creates jobs. Renewable energy benefits health through reduced air pollution. Fossil fuels face increasing financial risk. The business case for climate action strengthens as technology improves and impacts worsen. The economic transition is underway. Public awareness is growing. Climate concern has reached unprecedented levels, particularly among young people. Climate is no longer a niche issue. It's mainstream. This public concern creates political pressure for action. Youth mobilization. Young people worldwide are demanding climate action. They understand the stakes. It's their future. This generational push is powerful and persistent. Natural solutions exist. Protecting and restoring forests, wetlands, and other ecosystems can sequester significant carbon while providing co-benefits. Nature-based solutions are proven, cost-effective, and deployable now. International cooperation is possible. Despite challenges, countries cooperate on climate through the Paris Agreement and other frameworks. Climate conferences continue advancing. Cooperation is imperfect but real. Solutions create better futures. Climate solutions often improve lives beyond emissions: cleaner air, healthier diets, more livable cities, better public transit, preserved nature. The low-carbon future isn't just about avoiding catastrophe. It's about creating thriving, sustainable societies. Humans have solved big problems before. We've eliminated diseases, cleaned up air and water pollution, repaired the ozone layer, lifted billions from poverty. We've demonstrated the capacity for collective action on global challenges. Climate is the biggest challenge yet, but we have the tools, knowledge, and capacity to address it. The difference between success and failure is whether we choose to act with the urgency and scale the situation demands. The choice is ours. Conclusion. The molecule that matters. We began with a simple molecule. 1 carbon atom, 2 oxygen atoms. CO2 is invisible, odorless, and exists at concentrations measured in parts per million. Yet this trace gas determines whether Earth is habitable or frozen, whether civilizations flourish or collapse, whether ecosystems thrive or disintegrate. For hundreds of thousands of years, CO2 concentration varied within a narrow range, cycling with ice ages but never exceeding 300 ppm. Then humans discovered how to unlock carbon stored over millions of years underground. In just 2 centuries, an eye blink in Earth's history, we've increased atmospheric CO2 by 50%, to levels not seen in millions of years. This increase has committed us to significant climate change. We've warmed the planet by over 1 degree Celsius already. Sea levels are rising. Ice sheets are melting. Extreme weather is intensifying. Ecosystems are shifting. Coral reefs are dying. The impacts will worsen before they improve, even with aggressive action. But the story isn't over. Every ton of CO2 we prevent from entering the atmosphere matters. Every year of delay in peak emissions matters. The difference between 1.5 degrees Celsius, 2 degrees Celsius, 3 degrees Celsius, or 4 degrees Celsius warming is the difference between difficult adaptation and catastrophic impacts. The future isn't predetermined. It depends on choices we make now. The science is clear. The physics is well understood. The observations are unambiguous. The solutions exist. What's needed is will, political will, social will, individual will to implement solutions at the necessary scale and speed. Future generations will look back at this moment as decisive. They'll see either the generation that recognized the crisis and acted with sufficient urgency to preserve a livable planet, or the generation that understood but failed to act, condemning them to a destabilized climate. Carbon dioxide. This simple molecule has become the defining challenge of our time. How we respond will shape Earth's climate for millennia to come. The invisible gas has made itself the most important substance in our atmosphere, and dealing with it has become the most important task humanity faces. The Pacific had its pulse. Earth has its thermostat. And it's set by the concentration of one simple molecule, CO2.